Well, this is lecture 5 of basic calculus 1. So, in the last 2 lectures we had introduced the notion of functions and then given some examples of functions. So, in fact, that consists of repertory. Whenever we need some functions, we will take from them or even join them together depending on different domains. So, that is how they will be helpful for us. And today we will be considering the central idea of this calculus course, which is called the limits of functions. It concerns about the nearness of a point and how its the corresponding functional value behaves. So, suppose let us start with one simple example, simple function. F is a function from 0 1 0 closed 1 open interval union 1 to 2. That means, it is the interval 0 to 2 really, closed interval 0 to 2 except the point 1. Suppose f is defined on this and it is taking real values and it is defined by f of x equal to x plus 2. So, that is fairly simple function. So, let us consider this function. Now, the question we are going to ask is first notice f of x is not defined for x equal to 1, but then we can think of x to be remaining near 1 in either side, either it is less than 1 or it is bigger than 1, but it cannot be 1, f is not defined there, it is not in the domain. Suppose x remains near 1 and then where does its functional value remain? Well, f of 1 had it been defined with the same function, it would have been 3. So, naturally we would think that well when x remains near 1, f of x might remain near 3, that is what it looks. But what do we mean by this nearness? So, only after confirming what this nearness we are talking about, we can think of whether this f x remains near 3 or not. Well, that is a difficult thing because we do not know what is the meaning of near in real numbers really. What happens if you take 1 and you are scaling at here say 0 and this is 1, you may think near means it is somewhere here, but suppose I have taken a bigger scale like this is 1, but this is not 0, this may be say half, it is twice that scale, then that quantity which we thought near may not be any more near in whatever sense we have. So, what exactly we mean by remaining near? This is what we should first formalize. Well, we may think of instead of general near, we may think of how near or how close. Suppose I choose a point, say it is 0.9 somewhere close to 1, 0.9, I may think of it is near 1, but with some tolerance slightly more than 0.1. Within the radius of 0.1, I might accept all of them to be near, that is 0.91, 0.92 and so on. All those things can be taken as near. On the other side, if my nearness is something like 0.1, some quantification of nearness, then I would think 1.09 is also there, is also near 1. So, this is what we mean by telling how near, we say it is delta close. So, x is delta close to 1 means the distance between x and that point 1 should be less than delta. Obviously, I should take positive deltas only when I think of delta close. So, now our question will be something like, if x remains in this interval which is 1 minus delta to 1 plus delta, but x is never equal to 1. So, f of x remains close to what number and in how close, that is what we want to see. So, that means how close f x will remain to 3, it looks like it will be same delta because it is x plus 2. So, it is just shifting by 2 units. When this is x is near 1 delta close, f of x should be delta close to 3. That means, it looks like f x minus 3 mod should be less than delta. In fact, it is because we can find it out. If you substitute x plus 2 here, 2 and 3 gets cancelled, you get the same inequality x minus 1 mod less than delta. So, that is what we want to see in general, not only for this function. So, that means the question is, if x is delta close to 1, fx is how close to 3 in this case. That we saw it is delta, but in general it may not be that, it is just shifting, that is why it is happening. Suppose fx is x square, so it may not be that delta. So, let us allow even different closeness in the values of f of x. So, call that epsilon. That our requirement is now, if x is remaining delta close to 1, then f x should remain epsilon close to that number. So, in this case it is 3. So, in fact, our requirement is the other way around. We say that to make f x epsilon close to 3, I should take x delta close to 1. So, in this general sense of epsilon and delta, that is really our requirement. That means, we will say that f of x remaining close to 3, if x remains close to 1 in this delta sense, and that also epsilon sense. How close? It is epsilon close. Okay. So, that means, we would think something like, to make epsilon close f x and 3 to be epsilon close, we will say corresponding to each epsilon greater than 0, I do not know what is that epsilon. So, if I want that much close f x and 3 should remain, then I should be able to find out a delta such that x and 1 should be delta close. So, that means, x should be in the domain of the function with x minus 1 mod less than delta, but 1 is excluded, right. So, this is how it reads now, corresponding to each epsilon greater than 0, there exists delta greater than 0 such that for all x in our domain of f with 0 less than mod x minus 1 less than delta, this is your delta closeness of x to 1, then we should have f x minus 3 less than epsilon, that is f x will be epsilon close to 3. So, this is our requirement. We really abstract it to any function, not only for this function, and we should give a formal definition now. So, what do we do? Let us say our domain of the function d is such that it has a neighborhood around C inside D, right. So, possibly C is excluded, we are not interested in that value of C or whether f is defined at C or not. So, to the left of it there is an open interval which is contained in D, to the right of C there is also an open interval which is contained inside D. This condition should be holding because we need all points delta close to that C. Okay. So, now suppose L is a real number, we would say that the limit of f x is L as x approaches C. So, look at these bold letters, this is what we are going to define. So, in the earlier case our limit was 3, the limit of f x is L equal to 3 in that case as x approaches C. So, x is here and f of x values are on the y axis. So, we are telling C is here somewhere, x is remaining near C and L is somewhere here. So, you would say that f of x lying near L. So, that is what we say, the limit of f x is L as x approaches C, and we write also give a notation for it. Now, you can read the same way, limit of f x extends to C equal to L if and only if the earlier condition should be satisfied, which is corresponding to each epsilon greater than 0. So, you choose your how close f x should be L to, corresponding to that you will find a closeness in C that exists a delta greater than 0 such that for each x in D should be obviously in the domain with x not equal to C, C minus delta less than x less than C plus delta. So, it is within this, which we can write d delta of C. We may write this set as d delta of C, where this d is for deleted, C is being deleted, everything else the open interval remains, C minus delta to C plus delta, but x is not equal to C. For all those x, f x should lie between L minus epsilon to L plus epsilon, that is f x minus L mod should be less than epsilon. If this condition is satisfied, we would say that the limit of f x equal to L as x approaches C. So, look at something here, L is not given with f x, that we have to guess. So, once we guess on L, we can see whether this condition is satisfied for that L or not. If it is satisfied, L becomes the limit. If it is not satisfied, L is not the limit. Maybe possibly there is another guess, or maybe there is no possibility of any guess. Whatever L we choose, it is not possible. That can also happen. Okay. So, this is the central idea of the limit. Writing d delta c as the deleted neighborhood, c minus delta c plus delta, omitting that c, it says that each epsilon neighborhood of L must contain the f image of d delta c, deleted neighborhood. F of anything you take, it should be lying within that. That is what the notion of limit is. We will naturally take some examples and see how it happens. But this intuitive idea we should not forget, if x is near c, then f x is near L. And this idea gives rise to this formulation through quantifying this nearness or closeness. Okay. So, let us take say mod x. Mod x is a function. Now, it is defined from the whole of real numbers and its range is non-negative real numbers. We are asked to find out its limit, if possible, near 0. So, that is limit of mod x as x approaches 0. So, as it looks, mod x looks okay, if you remember its graph. So, it looks something like this. On the left side it is y equal to minus x, on the right side of 0 it is y equal to x. So, when x remains near 0 somewhere here, it looks that f of x is also remaining near same 0. So, our guess is that the limit must be 0 if it all exists. Now, you have to really verify whether it happens or not. Well, that means for any epsilon given, we have to get a delta such that the condition should be satisfied. So, here it looks that the same delta will do, because mod x is roughly equal to x or minus x. So, the distance from 0, if of x is fixed, then of mod x is also should be fixed the same way. So, we are trying to choose with delta equal to epsilon, see what happens. So, this is the crux of the problem, that we have to choose really a delta depending on the epsilon and that point 0. Here it is 0, that point c in general. So, this delta might depend on both epsilon and c, and that needs some experience how to choose. But let us see, this is coming from roughly looking at this function, how it is behaving like x or like x square, like what. So, it is roughly like x, that is why you are choosing delta equal to epsilon and trying to see whether it is satisfied or not. If it is satisfied, it is fine. If it is not satisfied, that will not say that it is not the limit. There can be another choice of delta. Okay, let us see what happens. So, with this delta equal to epsilon, now suppose I take x minus 0 mod is less than delta, that itself is epsilon. So, now I look for, under that condition I look for f of x and 0 difference. So, that is again mod x, and mod x is already less than epsilon. So, it says that if x minus c mod is less than delta with x not equal to c, then f x minus L mod is also less than epsilon. Therefore, this L must be the limit of f of x. So, limit of mod x, x goes to 0 equal to 0. So, this is how we are going to solve some problems, but in fact slowly once you get experience, you do not have to do all these things. You can see about this intuitive idea of nearness, how it will work. Now, let us look at this. So, f of x is given as 3 minus x if x is less than 1 and x square plus 1 if x is bigger than 1. So, at 1 f is not defined. So, that means f is defined or the domain of f is minus infinity to 1 open and union 1 infinity. At 1 it is not defined, everywhere else f is defined. Okay. So, we want to find out what is the limit of f x as x goes to 1. So, how do we see it? On the left side, if I take x is near 1, this is something smaller than 1, but it is near 1. So, 3 minus 1 is around 2, it is near 2. On the right side, if I take x is bigger than 1, so x square is still near 1 and 1 plus 1 is 2, both the side it is 2. So, my guess is that L should be equal to 2. Limit f of x extends to 1 should be 2. Let us see what happens. So, if you plot the graph, it looks like this is your 1. So, on the left side it is 3 minus x, this is 3 minus x. On the right side it is x square plus 1, and this point is omitted because at 1 the function is not defined. This is how the graph looks like. Again, from the graph it is clear that f of x is remaining near 2. So, that should be our limit. Our guess is that. Now, let us see what happens. How do we really justify it? You may think of justifying on the left side, you have to, for 1 epsilon you have to choose a delta, and on the right side again for 1 epsilon you have to choose a delta. Okay, let us choose it, check it formally. Suppose epsilon greater than 0 is given. Now, we choose delta equal to minimum of epsilon square root of 1 plus epsilon minus 1. So, it is very unintuitive. How did I choose this? You will see how this helps. So, only verification we can see. But anyway, so roughly it is on the left side, it is 3 minus x, it is shifting from x. So, delta should be equal to epsilon. So, that comes from the left side, and on the right side it is x square plus 1. So, if I substitute 1 plus delta there, it is 1 plus delta square plus 1 minus 2. So, that will be 1 plus delta square minus 1, and when I go to x, it will be square root of that. That is why this one is put, square root of 1 plus epsilon minus 1, to work with the function x square plus 1 on the right side of 1. But at this stage there is no need to see. Suppose we choose delta equal to this and see how it is verified. Now, you have to start with any x near this 1, which is delta clause, that is 1 minus delta less than x less than 1 plus delta, but x is not equal to 1. Choose, take any x within that. Now, on the left side the function behaves in a different way, on the right side different way. So, we break into two cases depending on the value of x, it is less than 1 or bigger than 1. So, let us consider the first case, say x is smaller than 1. So, this condition along with x smaller than 1 gives rise to 1 minus delta less than x less than 1. This is our assumption now. Under this we have to verify whether f of x, which is 3 minus x there, minus 2. So, their absolute value should be less than epsilon. Is it so? 3 minus x minus 2, which is equal to 1 minus x, and from this 1 minus delta less than x less than 1, it shows that 1 minus x is less than delta, right. Therefore, and delta is always minimum of epsilon or this. So, it is less than or equal to epsilon, hence this condition is satisfied. That is, if we assume that x is less than 1 and 1 minus delta less than x less than 1 plus delta, then we are able to verify f x minus 2 mod is less than epsilon. Now, you take the second case, say x is bigger than 1. So, in this case, with the assumption 1 minus delta less than x less than 1 plus delta and x is bigger than 1, we get that 1 must be lying between x must be lying between 1 and 1 plus delta. So, 1 is less than x less than 1 plus delta. In that case, we should verify our condition f x minus 2 mod. So, f x minus 2 mod here is x square plus 1 minus 2 absolute value, which is x square minus 1, that gives to 1 plus delta square minus 1. Now, delta is less than or equal to square root of 1 plus epsilon minus 1. So, 1 plus delta square minus 1 is less than or equal to this 1 plus, we just substitute that here, and that we simplify. So, 1 cancels and this gives 1 plus epsilon and again minus 1. So, that is epsilon. That is how we have chosen this, because this might work this way. So, you have to take care of the algebra, what is going to happen, and according to that we have to choose delta. So, sometimes what we do back calculation. If f of x minus 2 is less than epsilon is going to be satisfied, then what would have been our x? So, we come back slowly going from bottom to top, we would reach there. That is why this delta was chosen this particular way, minimum of epsilon and square root of 1 plus epsilon minus 1. So, we see that the limit condition, whatever condition is required, is satisfied. Therefore, we conclude that x minus 1 mod less than delta with x not equal to 1 implies f x minus 2 mod less than epsilon. Of course, with x equal to 1 something might happen, but that we are not concerned because f of 1 is remaining undefined. It does not matter also whatever value is defined for that event. Suppose f is defined on the whole of R, along with these two conditions we have f of 1 equal to 10. So, it does not matter because f of 1 is never used in this computation anywhere in the definition of the limit. Still, the limit of f x as x goes to 1 will be equal to 2, even if you define f of 1 equal to anything. So, it does not really matter whether it is defined there or not defined.